Hello everyone, welcome to this session where we get some science talks and actually find out what people have been doing with UKESM. I think we should crack straight on. So David's up first and he's going to tell us about sea ice and what we can do better, I hope. All right, so thanks, David. You've got about 10 minutes, I think, maybe some questions, and Hazel will tell you when you're nearly out of time. Go for it.
Okay, yeah, thank you. Good morning, everybody. I will show a bit of a comparison with observations of sea ice thickness and sea ice drift and use model simulations with a different kind of complexity. And for the models, I will show results from the historical UKESM simulation, from the physical core, historical and near future projections, and also force simulations, atmospherically force simulations with the same ocean and sea ice component, and standalone sea ice simulations force with atmospheric reanalysis and ocean climatology. So here on this figure, you see the mean ice thickness in April over this red area, which is the area for which we have continuously sea ice thickness estimates from Cryosat. With continuously, I mean from 2010 to 2000, also the last 10 years, for the winter, 7 winter months from October till April. And I show here the mean ice thickness over this area from the Cryosat over the last 10 years for April only. And this figure, so we see here this black line. So there is some interannual variability, but interestingly, the sea ice hasn't changed over the last 10 years, so there is no trend in this. For comparison from the UKESM historical run, these are the last 4 years, the ensemble is shown here. So there is, as for known reasons, a bit overestimation of the ice thickness. If you look at the physical core, there is the 4-member ensemble for the historical period. They're actually doing a pretty good job. And I also show here, there is a gap here, but this is just not connected. It would continue. These are the projections for member ensemble. Interestingly, we see here a sea ice trend decline that the Cryosat data don't show. And there's also here in yellow gold the forced ocean ice simulation with, of course, the reanalysis data, so we would expect to fit the interannual variability better. But there's also a bit of an issue. It doesn't really show that it does show a bit of decline, and the standalone ice simulation with ocean climatology is very close to the forced simulation, which is for April, and now show the same figure for November. And here, as again, the observations show in a way no trend, and here the trend is even stronger. The trend is in the forced ocean ice, also in the atmospheric forced ocean ice simulation, and in the physical core near future projections. Okay, let's look a bit at maps. Here we see the differences in ice thickness for November, this is from 2011-2014 mean, from the physical core against the Cryosat observation. So we see a difference plot here. So gray means it's fine, and blue color means the ice is too thin, and yellow color means the ice is too thick. And this is the same for the force simulation with atmospheric reanalysis. And it is noticeable there are some clear similarities in this, where we do have the strongest issue is in a way we get an underestimation here in the Atlantic sector with up to 1.5 meters, and which is the same in the not the same, but it's very similar in both simulations. So this indicates that the atmosphere is not really the reason, but it points more to stuff in the sea ice or its connections with the ocean. And I want to show here again, these are difference plots with observations for the ice drift. So we see in gray the ice speed is as the color response to the drift speed, and the vector shows the difference vector between the model and the observations. This is again, for the left here is the physical core and the force simulation, and again they are quite similar. So even though they are completely different atmospheric conditions with different wind speed, there are differences which are striking similar, so that the ice drift is a tiny bit too weak here in the Beaufort region. We get a bit of the drift speed is correct, but there is an error in the direction, and most strikingly the ice is drifting is much too fast here on the ice edge of Beaufort Sea and the Atlantic sector, and which is the same for in both kinds of setups. And a third point I want to show this is a bit about the pressure ridges and the thickest ice in each grid cell. So the ice is not homogeneous in each grid cell. We have different in each grid cell thinner ice and thicker ice due to formation of pressure ridges. And here we look at the fraction for each grid cell, which is thicker than 3.6 meters, independent from the mean ice thickness in this category. And the Kreisert observation over this area show that there's hardly any fraction of thick ice in October, and when it goes to more than 20% in April, whereas all the model simulations have hardly an annual cycle. So there is more or less the same thick ice is there the whole year round. Okay. What are possible ways to improve CR simulation, or what we can learn from this comparison, from these different kinds of complexity? Here I want to show an example about ice drift. So we have here for April, mean April 2011-2014, the observation, so which is the real ice drift from the observations here, and we have a default NEMO size simulation which looks like this. And we can see here that the ice drift is too weak over the thicker ice. Here the direction is a bit wrong, and here the ice drift is a bit too strong. And now what can we do to the sea ice to change things? So one possibility is to make the ice weaker, to reduce the ice strength. And we did this here quite a lot. So this is by a factor of 5 roughly. So if you reduce the ice strength, you get this drift pattern. So we can see here in this area quite a big change in direction, because if the ice is very strong, so it gives a lot of resistance to pushing for compression. So the ice is not drifting towards it. So we get quite a big change just from mainly decreasing the ice strength. So the pattern is much better, but we see obviously and we get here hardly any ice drift, and now we get quite a strong and the Beaufort Sea is quite strong, but the observation show is a bit too strong. So if we go a tiny bit only 3 times a week, 3 times weaker than the original one, when we get quite a realistic pattern. We did also make some changes. We use the form parameterization, so that means we don't have one transfer coefficient constantly for ice, but this depends on different contributions from pressure ridges, from ice flows, and we can individually tune them a bit to get a better drift pattern.
2 minutes.
Thank you. And here this is with respect to the thick ice. And you could argue, why do we care about this about this thick ice? But it has some consequences. So how we want to achieve, if you want to form more pressure ridges, one possibility is to make the ice weaker. That's why this is related to the stuff. If the ice is weaker, we get more pressure ridges and we get stronger formation. But we have a problem if you just do that when we form the pressure ridges, but we don't melt them in summer. So a big contribution is to actually make the heat transfer coefficients depending on the ice thickness. At the moment, they are all constant. So if you have this pressure ridges, it has the same heat transfer coefficient when a very smooth flat ice, and that's obviously unrealistic if you think about the shape of a big ice key that has a much larger area with the water is much rougher than a smooth level ice. So by actually changing heat transfer coefficients to make it dependent on ice thickness, so that the very thick ice, the ice melt is much stronger, and for the thin ice it's much weaker, we are able to get not perfectly the cycle what we observe there, but to make some improvement. And this also has consequences in a bit for melting of the very thin ice and for the unrealistic decrease we have seen in the last years. Okay, I show here the summary, but stop now. Yeah.
Cool, thanks very much, David. Very interesting. We've got time for some questions, and there's been a couple in the chat already. Colin, do you want to ask yours?
I can, yeah. It was just around this ice strength, David. Is it possible from observations in any way to constrain the ice, what you refer to as the ice strength, or is that something you can only constrain indirectly by its impact on things like drift?
I think drift is probably one of the best parameter to actually constrain the ice strength. I'm just wondering, where is I think the changes I show are, I mean, there are no clear constraints, so there is quite a big uncertainty in this. I went probably in the case where I showed the very strong drift, this is a bit over the top, this is too extreme, which is not reasonable. It was just more testing what is actually what the impact is. Yeah, but the ice drift is at the end the best way to constrain it.
Cool, thanks. And Evgeny's got a question as well.
Yeah, thanks. Thanks, Rob. Basically, I actually have a comment for Colin's comment and David's reply. That is absolutely correct. It's absolutely difficult problem. It's very similar to what Colin is like turbulent viscosity in the geophysical fluid dynamics. If you try to compare the measurements from the local sites, from the ice flow caps, for example, they do not match models at all. They're order of magnitudes, several order of magnitudes off, basically. So the local measurements of ice strengths do not match the large-scale geophysical strengths of the sea ice. And also the ice strength serves as a tuning parameter to some extent. It's not very well constrained because you have a combined processes of dynamics involved into that. So the answer is it's very difficult to constrain, and we don't think we have a at least good known publication actually trying to put some kind of range of that even. It's a tuning parameter, and also it changes with the resolution and forcing. That's another point. I don't know whether this makes sense.
No, thank you for the comment, Evgeny. Was useful. Just I would like to add that I think the point is the models use quite a high strength because this gives the best results as long as you have a constant heat transfer coefficient. Because if you use a lower ice strength, then and you don't melt the additional ice which forms in the pressure ridges, you get too much. You don't get rid of the thick ice. So in a way to avoid this is to have a quite a high sea ice strength. But by adding this new process, it is you will, by tuning the models, you will come up with a reduced ice strength, which gives realistic results. Not sure whether it was. Could you understand what I mean?
Yeah. Thanks, David. Actually, I got a question. Sorry, about the.
Well, actually, can we? I think. Sorry, Evgeny. Can we move on in the interest of time?
Yeah. It's on the chat.
Yeah. But yes, feel free to put it in chat and ask David offline as well. Okay, so next we've got Antony Siahaan, who's going to talk to us about some results around the ice around Antarctica.
Can people see it? Well,
yep, looks fine to me.
Thank you, Robin. So I'm going to show some results from the scenario projections of from the coupling between the UKESM1 and the bicycles models, or also called the UKESM1 ice. So I will start with for people who are not aware of what's the difference. So I will show some difference between the UKESM1 and UKESM ice in the Antarctic region. So on the left-hand figure here is the horizontal view of the domain in the UKESM1. So the white area is the Antarctic. So and this the vertical section of it. So the border between the ocean and the ice, all the way down from the top. It's represented by the solid ice. So in UKESM 1, this domain stays constant; it doesn't change. And in reality, the Antarctic region is surrounded by ice shelves, probably about 80 to 90% of them. So this should be under this ice shelf should be a cavity where the ocean can enter. So in UKESM 1, the melting of the ice shelves is represented by a parameterized value which is nearly constant during the simulations, and so it's only the impact is only one way, the melting from the ice to the ocean. So there is no change of the topography that the ocean can see. Whereas in the UKESM 1, we open this cavity, and this is the horizontal view of the bottom profile. So it's now open. So by simulating the ocean circulation in the cavity, we can get the information of the temperature and the salinity, and then NEMO is able to compute the melt rate directly, and with the available vessel forcing from the bottom and from the top, from the and joules in SMB and temperature. Now we can employ bicycles to evolve its topography, and then give the information to NEMO to adjust its domain. So we do this coupling annually every year. So the other difference between the two models is in UKESM 1 ice, we don't use the Medusa in order to reduce the computational resource. And this is a thing that we are currently trying to add at the moment. So given this annual coupling, now we are able to directly simulate the sea level rise projection. And so for this projection runs, we choose the lower resolution N96 and Orca 1 configuration. And we choose the most aggressive scenario and the greenest scenario to see the impact of the radiative forcing anomaly. So for each scenario, we use a small ensemble of 4 members, and running from 2015 to 2100 for SSP1, and an extension of 15 years is given to SSP5 just to confirm the climate signal, which only starts to appear at the end of the 21st century. So for the ice shelf melt rate, in the modern observations show that the ice shelf melt rate is dominated by the western region, in particular the small ice shelf near around the Amundsen Sea and Bellinghausen Sea, whereas on a big shelf, Ron-Filchner and Rose around here, it doesn't show a big red. So the most concerning is around here, and then the bigger melt rate may lead to a bigger ice discharge from the grounded area, which can increase the sea level rise. So in the first 10 years of the simulation, on the top left here, we managed to capture the red and blue color in general, and in the SSP1 until the end of the simulation, which is given by the top right here, there isn't much significant change in the melt rate, whereas in the SSP5 we see two events of the strong melting, and so this on the bottom left is the last 10 years of the 21st century melting. So the region in the Rose region, the strong melting starts to develop in the 2070s, and after 30 years, the warm water access the furthest south, whereas if we see on the other big shelf, Ron Filchner, the red color starts to appear here. So for the 15 years extension, we confirm the warm water incursion into the ice shelf, which leads to strong melting as well. So that was the pattern in the map. So for in the integrated melt flux, here the black color is for the SSP1, the dash line means the ensemble member, and the solid lines is the ensemble mean. And the red line is for the SSP5. We see that for members from each scenario, they all follow similar trajectory, where then for the total, the black line is slightly below 1,000 gigaton per year. So it is below the modern observation, which is from 1,100 to 1,500 gigaton. So the strong melting can be seen in the bottom two panel here for Rose around 2070 and Filchner at the end of the 21st century. So that's what happened on the bottom. So over the top, the surface mass balance on the top left panel is given by the mean of all ensemble member, and the right hand side is the difference in SSP1, the difference between the last 10 years and the first 10 years. So if we compare the color and the color scale, we see that the difference is not that significant. But in the SSP5, the difference is very apparent here, where the area around ice shelves show dark blue and the grounded ice show dark red. So that means a negative SMB on the ice shelves and highly increasing SMB on the grounded ice. So what is important for the future sea level rise is the change on the grounded ice. So this red thing. So so to see what caused the difference, the diverging response of the SMB in different area, we break it down into different components.
2 minutes.
So the change of the SMB on the ice shelf, which shows very negative in the SSP5, is caused by the melting and the runoff, which is very strong here. And whereas on the grounded area, the highly increasing SMB is caused by strong snowfall. So this shows the integrated flux of the ice budget. So on the top is the integrated SMB, as we showed in the previous slide, that in SSP5 the SMB is increasingly highly in the last 50 years, whereas in the SSP1 it stays almost similar. And with the too strong melting event in the SSP5, we may expect a high ice discharge from the grounded ice, but we don't see that very clearly until the end of the 21st century. We only see a slightly increasing pattern here. So that's 2070 when the Rose melting starts to occur. So at the end, the SMB dominates the ice mass budget, which leads to sea level drop for the SSP5, whereas in SSP1, the black line, it's still slightly below the modern observation. So some of the summaries of the simulation is that we managed to perform a stable coupling until the end of the simulations, and that the ensemble members follow similar time series pattern until the end of the simulation. For SSP1, all the budget are slightly below the present observation, and we see some strong strong climate signal in the SSP5 for the ice shelf from the top, and a strong melting from the top and the bottom, whereas in the grounded ice, the high SMB occurred, which leads to sea level drop. But because the ice dynamics is very slow in the Antarctic region, so we may need to perform a longer simulation to see the effect of the strong melting on the big ice shelves. Thank you.
Cool, thank you, Anthony. We've got some questions in the chat. I'm going to suggest, Catherine, can you ask your question? Even though Paul's made a comment, but I think it would be good to air that widely.
Yeah, I find it's very interesting that there is a pattern at the end of the century in the worst case scenario in the Filchner ice shelf, because it's very important for the recovery area that has been shown to be very sensitive to what happens in the Filchner ice shelf, and that can go into a marine instability. And I think it's a very, I agree with the comment by Paul that it's due to the fact that the USA is going below the ice shelf, while none of the OGCMs in ISMIP were doing that. And I think it's very important to continue for the next centuries, or maybe 2 centuries, to see what happens, because it's really crucial. It goes, there were a long time ago a paper by Hartmut Helmer about that, and I think it's a crucial point for the protection of Antarctica.
Yeah, for ISMIP projection, they mostly use the currently available CMIP output, which do not include the cavity circulation in the cavity. So they extrapolate the temperature and salinity from the nearby the nearby ocean. So I think that depends on how they perform the extrapolation. So I think I also noticed that the melting is very high in some of the ISMIP projection, whereas in our simulation for Filchner, it only started very late, and some of the ISMIP shows very high, maybe even from the 2050s or 2060s. So the interaction between them will be important.
Yeah, I think it's important that something may be happening at the end of the century. It's an important result, and it's thanks to the fact that you have a fully coupled circulation below the ice shelf. And I'm impressed by this result, and I hope you will continue the simulations to see what happens next.
Thank you.
Cool. Thanks for that, Catherine. All right, well, we should move on. So next up, we have Vicky Lee, who's talking about ice sheets again. Excellent.
Okay, lots of ice sheets today.
Thanks, Vicky.
Start this going. Okay, so stop. So what I'm going to be talking about is essentially what's the difference about the control run in UKESM1.ice with an interaction with Greenland, with an interactive Greenland ice sheet. We don't have the ocean forcing that Antony has. So it's just Greenland forcing, no Antarctic interaction. So what you see in this plot is the surface salinity averaged over the North Atlantic, and it's a 10-year rolling mean that you're seeing. So the red line is the interactive run. The blue line is the same control run, but with a static ice sheet. And you can see that pretty much they're very similar, except for these two regions, which last about 50 years, and they're separated by 200 years. And the freshening in these two periods is very strong. I've included the salinity from the PI control. This is from UKESM proper. We're looking at GC 3.1, but the UKESM pre-industrial control is much longer, and we don't see the same freshening in that run that we're seeing in the interactive control. So the controls share lots of interactions that are commonly seen in Atlantic multi-decadal variability, but we don't get the characteristic 50 to 70 year period. Ours are more like 200. So the other thing that's observed is that there's been great salinity anomalies, which is freshening of the Atlantic rather than increasing salinity. And they've been observed in the 1970s, 80s and 90s, which aren't fully explained. So we do see freshening, but whether they are great salinity anomalies, but it's interesting. So a mechanism that's common to both the multivariable, multi-decadal variability and the GSAs is the Arctic mechanism. So what I've done in the plot on the right is an average of the sea surface salinity over the second period of the second anomaly, and then taken that away from the background salinity. So you can see that in the North Atlantic, we get strong freshening. And in the previous plot on the left, I've taken the salinity average over a 40-year period at the start of the anomaly. And we can see that there's freshening in the Arctic that's making its way into the Greenland's gin seas, and then it's making its way down into the North Atlantic along the East Greenland current. And these anomalies seem to end when more saline water follows the same path from the Arctic down into the Green Seas and into the North Atlantic, and also the salinity coming in from the south as well. So this mechanism is not necessarily connected with the Greenland ice sheet. So what's different about the interactive run that's not in the static run? So in the static run, we have constant in time carving from Greenland. It's not constant in space, but it's constant in time. And in the interactive one, that varies by about 62 gigatons across the run, which is not very much at all. But that carving is used to seed the iceberg model in NEMO. And you can see that the icebergs drift all around Greenland. They mostly stay close to, melt close to the Greenland land, but they do make, a lot of it makes it into the North Atlantic and also into the Greenland seas around Iceland. So on the right, we've got time series of the melt in the North Atlantic. The blue line is the static control and the red is the interactive. And I've got it for the North Atlantic and for the Greenland gin seas as well. So the thin line is the annual variability and the solid line is the 10-year rolling average. As you can see, there's a lot of variability in the melt that isn't in the carving. I've also marked in the vertical black lines is the period of the freshening in the North Atlantic. And we can see that the increase in carving in the interactive run mostly finds its way into the North Atlantic. But what is interesting as well is that at the start of the anomaly periods, there is an increase in the melt each time. And this is particularly noticeable in the gin seas around the second anomaly. There's a big spike in iceberg melt Of course, the vertical scales are a bit deceptive. That makes the green one a lot more than it appears in the North Atlantic. But what you can see, round about 2,200, that the iceberg melt decreases in the North Atlantic, but increases in the June seas. This may be because the icebergs that go into the North Atlantic have drifted back into the June seas around Iceland, or the amount of buildup of sea ice is preventing the icebergs travelling down the East Greenland current, and they're drifting into the June seas instead. So what's interesting about the North Atlantic is that this iceberg melt is well correlated to the variables that interact in the multi-decadal variability. So they interact with the ocean property variables and the atmospheric variables. Whether they're drive, cause, or effect, we can't say, but there's definitely a connection there. So it's all very well to say that icebergs are doing something in the control run, but what about in reality? So I've pieced together two figures here. The top one is the observations of icebergs near Newfoundland, which is the pink circle in the location plot, and the observations of the solid black line. And below is summer salinity in the region shown off the west coast of Greenland, and the sea ice. So negative values of sea ice means there's a lot more sea ice. So what you're seeing is that the great salinity anomalies are marked with the big thick arrows, that there's definitely more icebergs crossing near Newfoundland in that period. But what's interesting, I think, is that the few years before each spike, there is very little icebergs crossing the threshold.
2 minutes.
Thank you. So what could be happening is that either the circulation's changing and the icebergs aren't making it to the observational site, or they're melting a lot more and they're melting in the North Atlantic. So what else is different between the two models that's maybe important is that I've put the iceberg melt again at the top, and just below that is the maximum mixed layer depth in the Labrador Sea. Again, I've included the annual means in the thin line and the rolling average in the thick line. And what you can see is during the period of the freshening in the North Atlantic, you're getting less mixing. The mixed layer depth is smaller. But what's also interesting is that the interannual variability is more suppressed. This is not a feature of the static Greenland control. And that seems to make the difference, because there's lots of interactions going on that are creating the interactions that are creating the salinity options, and at the same time they're suppressing the mixing. So with suppressed mixing, this allows salinity that's either coming from the Arctic or coming from the iceberg melt to accumulate. And critically, the icebergs may not have a lot of freshwater flux, but what they are doing is they're drifting into sites of deep convection, and they seem to be giving the freshwater flux where it's needed. So basically, to answer the question, can icebergs carved from Greenland's glaciers explain North Atlantic freshwater anomalies? Maybe not, but I think they are interesting because the changes in salinity are caused by the Arctic mechanism, but the iceberg melt certainly enhances anything that's going on. Thank you.
Excellent. Thank you, Vicky. We've got a couple of questions in the chat. Colin, do you want to ask yours?
Sure. I was just wondering, after those periods of freshening and the periods where the mixed layer depth drops substantially in the Labrador Sea, is there a response in the AMOC at all? See a change in AMOC strength?
Yeah, so the AMOC weakens during those periods. I mean, it doesn't, the AMOC is the same, virtually the same in both these static and interactive runs, but during those periods, it's a lot weaker. It seems to follow the change in the mixing rather than leading anything. What's also happening is in those periods that there's less heat coming from the south, and that seems to be causing cooling in the North Atlantic as well.
Cool. Okay, thank you. There's a couple of other comments in the chat you could have a look at, Vicky. But can we move on, please? Chantelle, are you ready?
Yep, I'll share my screen.
Cool. We're going to move away from the ice now and have a couple of talks about fire.
There's a whole fire and ice joke you're missing there, Robin.
I'm very deliberately missing the fire and ice joke. Sorry, people.
Okay, can you see my screen?
Yep, you're good to go.
Great. Thank you. Okay, so I'm going to be talking about some work that we've been doing recently, looking at fires using the Inferno model in JULES and the impacts on the carbon cycle with future emissions and looking at SSP emission scenarios. We're specifically focusing on South America for this piece of work, which has been recently accepted for publication in Climate Resilience and Sustainability. So just to start with a little bit of context of why we're interested in looking at this. So we're already seeing some shifts in the fire regimes in South America, but the confidence so far in future projections of fire is low. From IPCC AR5, we had quite a few models looking at this, and especially with all of the interactions and feedbacks feedbacks onto the carbon cycle. And that means that there's quite large variation and not too many data points for us to be able to draw from. There's also a lot of disagreement in future projections of rainfall over this area. And the other big driver is that UKESM1 doesn't include the fire vegetation interactions with the carbon cycle at the moment. So these runs have been done offline so that we can look at those impacts. We use global warming levels to look at the difference between future and present day in this paper. And we ask the question, how much fire-induced carbon loss will there be over South America at different global warming levels in the future? So we use JULES, which is the land surface component of UKESM, and we use the climate forcing from UKESM so that we could look at the future scenarios of change. So that means that we use the JULESES configuration. It's got varying land use change from CMIP6 and the 13 plant functional types that we use in JULESES. We've got an historical period of 1860 to 2014, and the future period runs from 2015 to 2100, and we looked at 3 SSP scenarios, so SSP 126, 370, and 585. We look at the change from present day for 4 global warming levels, 1.5 degrees, 2 degrees, 3 degrees, and 4 degrees. And a quick reminder for those who aren't familiar, we use the Inferno fire model to calculate burnt area, and that uses ignitions from population and lightning data, and flammability from the fuel, from joules and soil moisture, and then inputs of precipitation, temperature and humidity from the climate forcing. And it also is coupled to dynamic vegetation through TRIFID, so that we get feedbacks onto the land surface with vegetation mortality and litter burning as well. So to start with, a bit of validation for the model. So in the top left, we've got plots of bias, present day bias compared to observations for temperature, precipitation and biomass. We can see there's a little bit of a warm bias in over South America. For precipitation, there's a little bit of a dry bias in the northeast, and this has an impact on the distribution of biomass that we see in the model. So that you can see there's a little bit here where we're seeing negative bias in biomass in the northeast, which is possibly linked to this dry bias that we're seeing for the UKESM climate. Also, there's quite a large positive bias in biomass, so we're getting too much forest over this area, which has been quite a long-standing problem. That's helped a little bit when we include fire, but the trouble is with this forcing, we're seeing a bit too much fire in the northeast because of this dry bias. So that's slightly different to the pattern that we're seeing with the offline runs driven by reanalysis of crude JRA, where the fire sort of distribution is much closer to what we see in the observations. So it's just being aware of that bias in the burned area that we're seeing due to the drivers here. So in terms of the results, so we started looking at some of the drivers for burned area in terms of temperature. So as we would expect, increases with the SSP scenarios over the time period of the run. It varies slightly, but pretty much at 4 degrees, we're seeing warming everywhere over South America. Precipitation's a bit more variable, but we do see at the higher levels of global warming a very strong sort of drying over especially the Amazon basin, but more of a wetting signal south of that. And then, so looking at the impact of that on burned area, if we look at the burned area and fire emissions for the time period up to 2100, we can see in SSP 585 and 370, so the stronger warming scenarios, there's a big increase over that time period in both burned area, which is the solid line, and the emissions, which is the dashed line. A bit more stabilized in SSP 126, but still an increase from present day. And then this is presented on the right-hand side by global warming level and SSP scenario. So again, you can see at the higher levels of warming, there's a strong increase in burned area, especially over sort of Amazonia and the just south of that, the arc of deforestation. Not too much difference between the SSP scenarios at the different warming levels. There's slight differences that you can see here at the lower levels, which may be due to differences in aerosols or the timing at which the different warming levels are reached in each scenario. So moving on to the impacts of the fire on the land cover and vegetation carbon. So on the plot on the left here, we've got vegetation carbon for South America in gigatons of carbon. The dashed line shows the runs without fire, and that stays pretty level into the future. So we're not seeing too much change. The main changes that you can see here are due to land use change in the south. However, when we include fire, then there's a big change, and we're seeing a big decrease in vegetation carbon into the future, especially with SSP 585, the stronger emission scenarios. And you can see that spatially that it's really a lot focused quite a lot over Brazil, but really sort of affecting most of the continent. This is a change from present day with fire on at the 4 global warming levels again. Also in terms of GPP, the productivity is affected. So the increase in productivity that we see here in SSP 585 and 370 without fire, the dashed lines, due to the increase in CO2 fertilization, that's actually counteracted by the increase in fire, so that all the scenarios remain approximately the same level of GPP in the future. So I think that's quite an important point here, that when we include fire, it's counteracting the CO2 fertilization effect.
2 minutes.
Great, thank you. The other thing that is of interest is, although this work doesn't feed back onto the climate, so these are the offline JULES runs, so we don't get the feedbacks onto the climate with fully coupled UKESM. But we do see that there's a further reduction in evapotranspiration resulting from the fire vegetation coupling, which is shown in this plot here. The fire on shows that there's additional evapotranspiration decrease at the different warming levels. So this suggests that there could be enhanced drying in this region when fire is fully coupled to the atmosphere, and that's of particular concern over Amazonia, where evapotranspiration and moisture recycling is a significant source of precipitation. So there could be some additional feedbacks there. And so just to summarise, we've been using UKESM on climate projections to look at burned area with JULES run offline, and this increases the burned area with higher warming and higher emission scenarios. The fire vegetation feedbacks suggest that there could be a loss of tree cover, vegetation carbon and productivity with those warming scenarios. These fire vegetation feedbacks are not currently represented in UKESM1, and so it suggests that there could be large impacts on future projections of the carbon cycle as we start to into UKESM for UKESM2. I'll stop there. Thank you.
Great, thanks, Chantelle. Very interesting. We've got a couple of questions. Ranjini, do you want to go?
Sure, thanks, Robin. Nice talk, Chantelle. I was wondering if you looked at seasonal changes. Did I understand correctly that these were annual changes? And does it make a difference? Like, do you consider like both changes in climate and burnt area on a seasonal basis? I ask because some of the changes at 5 degrees and stuff are different across seasons, like in climate, as you know from our analysis. So I was just wondering if that makes a difference.
Yeah, in this study, we just looked at the change in over sort of 20-year annual mean, so we haven't really looked at the seasonal changes at all. I think I started to look at it, and it showed that when I was looking at precipitation, that drying seemed to be throughout the season, but I'm sure there's a lot more that we could look into with that. That would be interesting. We're hoping to do a follow-up paper to this that looks at global scale rather than just focusing on South America. So that might be something we pick up in that.
Sure, thanks.
Cool, thanks. Colin, do you want to ask yours?
Okay, I think you touched on it already, Chantelle. But a large burnt area is going to potentially change the vegetation type when you couple. Is UKESM, as it stands now, able to make that kind of interaction and coupling when you have fire in, do you think?
So we're starting to do the fully coupled runs, and the initial results show that there is quite a strong change due to fire. So we're working on tuning that at the moment to try and see if we can, even in the present day, we're seeing the strong interactions and feedbacks with the climate. So I think there's going to be a bit of work to do to try and get the present day looking as good as we can, which is what we're working on at the moment.
Cool, thanks very much. All right, so for our last talk of the day, Doug's gonna tell us some more about fire.
Hello.
Not last talk of the day, sorry, last talk of the session.
I might put you to sleep. It will be the last talk of the day for some people. Anyway, okay, yeah, observational constraints. Is that what I call it? Observational constraints on future shifts in fire regimes using these models. Some of these results are very brand new, like early hours stuff. So a bit of surprise for me as well. Well, we'll figure it out. Okay, so so we're not the only kind of modeling group trying to get fire into our system model. There's a few others, and some of them tried so hard they managed to get it into CMIP 5, which is showing up here. And Foster and Nuslop did a bit of analysis on fire in these system models and looking at climate to fire interactions and trying to kind of evaluate how good they are. So here's just a map of present day burnt area for the 5 different ESMs of firing for CMIP 5 compared to observations, which is GFED4 on the bottom right. And you kind of squint and they look kind of okay. Some of them do anyway, but there is some kind of quite big differences between the models and observations. Some of them common, like the East Africa problem isn't just something that we've got, it's something that all models have. But some of them are just kind of like a random mess between models. And that plays out in kind of future projections of fire as well. So you have these kind of future projections of global burnt area at the top row and then fire emissions in the bottom row from all these different models. And there's a big disagreement between what's happening today and what's going to happen in the future, including like how the trends in fire emissions into the future as well. So some models say it might go down a little bit, some models say it might go huge amounts. And I think every paper which is trying to do future fire projections kind of finishes with a similar sentence to the one I grabbed from one of my papers. You know, that fire-enabled DGVM has known biases in the simulation of vegetation, fuel load, and burnt area, and often climate as well, which means that we're just kind of presenting a possible result rather than something which is actually definitive. So that's kind of what we're trying to aim to try and tackle a little bit here. So if we can get a model with the best possible parameter combination, which we get by training to historic observations of burnt area and climate, and take into account remaining biases in the climate, vegetation, and the fire model itself, is there anywhere where we can actually say something about future changes in fire regime? And to do this, we're using a couple of new tools. Camilla has done loads of work at trying to get ESMIP. At the moment, it's ESMIP 2B, which is working on ESMIP 3 as well. ESMIP fed through JULESES, and we also have the ConFire Bayesian fire modeling framework, which a few of us have been working on as well, which helps track parameter uncertainty and model error. So just a very brief overview for people who don't know about ESMIP. It's been mentioned a few times in this meeting, but it's basically, for our purposes, it's a multi-model climate ensemble. For 2B, which is the one we're using here, it's 4 models, and it's bias corrected to present day. And that bias correction is then propagated into the future to have a nice seamless transition from present day to RCP 2.6 and 6.0. And we use those climate for historic input and future projections to drive JULES, which gives them information about fuel, and then we use ESMIP climate and JULES fuel to drive ConFire. And ConFire is a super simple fire model, which I'm going to make sound really complicated now. It takes veg cover and soil moisture, which is the stuff that comes from JULESES, precip, humidity. Actually, humidity might come from JULESES as well, I forget. Anyway, from ESMIP 2 and outputs from ESMIP 2. And at the moment, we're keeping lightning and population density constant, but we might hopefully going to fix that in the future. Those get fed through into to 4 controls, and it's just very simple linear combinations of those inputs into those 4 controls. So we have fuel load, flammability, how dry or wet the fuel load is, ignitions, and human suppression. These are then kind of just have a simple logistic transformation of these controls, which describe the maximum burnt area you might expect given the value of a certain control. So if you had 50% fuel continuity from a fuel load, it would say you'd have between 30 and 50% burnt area if all of the conditions were perfect for fire. And multiply together to get burnt area, and that's just a 19 parameter model with 2 parameters, so it's nice and simple and computation efficient, which is important because Bayesian inference, the technique we use, is computationally like exhausting, and it started off being unfunded, so it was only sneaky supercomputer time. So to get the best parameter combinations, we've trained the model fed with ESMIP inputs from each of the 4 participating models into ConFire and train that against GFED4S, which is historic observations of burnt area, and the map on the right. That maps the probability distribution of the model parameters, and these parameters can co-vary with each other. So it's kind of trying to map the full parameter space. this is not quite a full map, but a map of all the parameters right on here on the right, and then this one's bringing up 2 key parameters: fuel discontinuity point and moisture extinction, and looking at the reddy purple stuff is the posterior solution to the model, probably distribution of the parameters, and they have quite a large range, like suggesting you have a fuel discontinuity point of 10 to very big, and same with moisture extinction, but they co-vary for each other, so the actual kind of range in parameter space can still be quite small. And we use these constructed probability distributions to look at changes in fire by 2100, just by feeding in the future climate and fuels from EasyMIP and JULES using the same parameter set. So the reason why the Bayesian stuff is super useful under for fire is that under the same bioclimatic conditions, so I've given a quick example here of intermediate fuel in really dry conditions, you can actually have all sorts of burnt areas. So I've just grabbed these conditions from somewhere in South America over a period of time. You can have plenty of places where you get very little burnt area, and then plenty of places where you get huge burnt areas, and it's a little bit random. And when you're using a normal model, so like say Jules Inferno, you're kind of forced to make a bit of a pragmatic parameter selection, which will give you a single value for a burnt area, which if you're trying to go for the average burnt area for this bioclimatic conditions, could be somewhere in the middle where you don't actually see any burnt areas at all. By using the Bayesian approach, you can actually get a nice kind of distribution of potential burnt areas, which covers all the potential ignition, fire events. And I should say that these listings get spread out based on the model error that we kind of propagate through as well. Don't we understand that completely, but the same messages like climatic variables, we have a range of possible burnt areas, and that's how the model runs. And then for trying to assess the significance of future projections in burnt area, we basically compare probability distributions for historic, which is shown as an example in the grey, and then the probability distributions for each model and each RCP into the future. The actual burnt areas distributions don't look anywhere neat as this, but it's just trying to get a bit of an example. And one possibility is that you get a big collection of messy future distributions of burnt area for a given grid cell, and you can say that actually our fire model error, which kind of is capturing the spread of these distributions, isn't small enough to say anything about how whether fire will significantly change in the future. So we can't say that those areas we can't say anything about. It could be that we can be super confident in all models and RCPs, which all go in the same direction, and say, right, we definitely know fire is going to change this way. So that's cool. That's the best case.
2 minutes, Doug.
Oh, cool. Okay. Oh, I'm not doing too bad. I'm going to be a little bit over. And then, but what's also more likely to happen is that you can say that the fire model has small enough errors to say that there's definitely going to be a change in burnt area, but there's a bit of a mix between models and RCPs about which direction might be. So you kind of say, we know burnt area is going to change, but we don't know how. And it could be dependent on model selection or RCPs. So here, for example, both models say that RCP 6 will show an increase in fire, and RCP 2.6 will show a decrease in fire. So your emission scenario is important about what the future fire might look like. And that brings into one final one as well, is that there might be a situation where your choice of emissions scenario, so how you mitigate future emissions, might be able to significantly reduce the impact of burnt area as well. And these are all just done by a simple metric which compares the probability distributions of present to future. So this is just a straight projection of future burnt area change by the end of the century for the two scenarios compared to present day. So if you just look at this map, you can see it's quite messy. So red areas say that all models agree that there's going to be an increase in fire. Blue says all models agree there's going to be a decrease in fire, and purple says that models could be all over the place. And a lot of it is purple, so you could say some models saying there's going to be an increase and decrease for the two emission scenarios. But if we start looking at significant changes, then it starts pulling out some kind of quite interesting features. So here in the red in the high latitudes, there's lots of places where there's a significant, we're projecting a significant increase in burnt area. So our probability diffusions don't match up, and all models agree for the respective RCP in the direction. And again, the blue area down here is the same kind of thing. and you can map these uncertainty regimes and calling them out. So you have white areas here where the model area is so big that we can't say anything about the projection of future to the end. And then coloured areas are whether there's a significant change, but compared to the fire model error, but climate and RCP might change it. And then there's climate and RCP, and ones where all climate and RCP models in the red either say there's going to be an increase or a decrease in fire. And I'll skip over this, but because it's got controls in, you can look into this paper when it comes out at the bottom at the controls driving. So the answer to the question is like, yes, we can say stuff about how fire might change in some places by the end of the century if we get the best parameter combination and take into account errors still. But there's a few caveats to this. We're still using present day emissions. We're only using one model, although FireMap's going to be doing multi-model runs, I think, at some point that Chantelle's leading, which means we might be able to use more than just JULES. And the big one is there's no biogeochemical feedback from this yet, although we might be at some point. So things like the last presentation are still super important until we get that fixed. Right, yeah, done. Thank you.
Cool, thank you, Doug. We're a bit late already for lunch, so there's a couple of comments in the chat you could look at. But I think I'll call the session to a close there. Thank you everyone for your talks, super interesting. Keep talking to each other in the chat. I'm going to